course, because you've hit upon one or two very important points of inferential statistics right here. Go back to your 1 prop z int. Carly, we're leaving it at 99% confident because it's awesome. I love it. Okay. 1 prop z int, even though people use 95 usually, and there's a good reason for that. We'll come back to it. Well, there's a good reason and a crappy reason. We'll come back to those reasons. Now, remember how we had 160 out of 340? Let's change that 68 to 99. Now, would you do this for me? Double both x and n. Make them both twice as big as they are right now. So 160 becomes 320, 340 becomes 680. 680, right? Is that right? 680. Now, when I press calculate, tell me what's going to happen. Tell me what's going to happen. What's going to stay the same and what's going to change? What's going to stay the same and what's going to change? What? I have a vote for p hat is going to stay the same.
Yes.
Does that make sense?
Yes.
Makes perfect sense. P hat is x over n. If you double x and double n, it's like you didn't change anything as far as p hat goes. That means the center of our interval is still going to be at what number? 47%. Still at 47%. So what's going to change? Yes! Boom! Look at that p hat. 0.47. Exactly the same as it was before. But look at your margin of error. We shaved some percentage points off of both ends, didn't we? We just illustrated what Veronica was talking about. If you replicate a study, and a huge if, here's a huge if, your center stays the same from your previous study to this study. That's a big if, isn't it? Yeah. Isn't that a big if? We assumed the 47% would then stay in the next study. What if it varies a little bit, goes to 45 or 48? We saw that, even in my results right here, we see that. The overall average is 44%, overall thousands and thousands of trials. But it does vary from trial to trial, so there's a big assumption that it stays the same. But if we can reasonably assume that, our margin of error just shrank down, legally, yes? Replicate it again, go back, do it again. Stat, test. Stick a 0 on the end of both of these. Is that going to change p hat at all? Is that going to change p hat at all? No! P hat is going to stay 47% because you're increasing the numerator and denominator by the same factor, therefore it cancels off. Yes. But all of a sudden, we now have legitimate, statistical, significantly different results than a coin flip, don't we? We now are statistically significantly different than a coin flip because we saw the result enough times. Natasha, what's on your mind?
You can't just do that, though.
No. I'm saying if we got these results.
Oh, okay.
If we replicated the experiment this many thousand... No! God, no! Sister! I'm trying to answer Veronica's question with if we got this data. If you... Jesus, no. Yeah, if I did that... Don't publish that. No, you can't just do that. Of course not. But what I'm saying is, you can get the exact same p hat value, but if you see it over of trials, it becomes statistically significantly different than an assumed parameter value. You can't just make it up. Well, pretend that it 10,000 times. Totally fine. Totally fine. It's great. Pretend that. Good luck publishing. Good point. Good point. My point was the replication idea. And there is a big assumption in there, isn't there? The assumption is that it stays 47% the whole time. Now, it actually looks over time like it's closer to 44%, at least based on the data I've collected in these classes. So, I mean, who knows? I just love collecting the data because I love seeing what happens. That's my personal favorite thing, just keep collecting the data and see how it comes out. Yeah. Say that again? That's okay. The one up top is a combined sample of everything. Yeah, exactly right. Which comes back to Stefan's question. What does it really mean when we say we're 99% confident? What does that really mean when we say